Now the next thing I want to consider are correlations. Correlations. This shows the relationship between two sets of variables. So as one thing varies, something else will vary, and a correlation will show how these two characteristics are related. And I think probably the best way to do this, again, is to use graphics. So let's look at some graphics that show correlations. But before we do that, I'll just tell you one thing about correlations, and that's the way they are measured. Now, with a correlation, a perfect positive correlation we record as a +1. And a perfect negative correlation we record as -1. If there's no correlation at all between the two variables, then the correlation score on that would be a 0. So 0 is no correlation at all. -1 is a perfect negative correlation. +1 is a perfect positive correlation. So between those, -1 and +1, obviously there's any amount of possible ranges. So you can have a positive correlation of 0.5, 0.6, 0.7, 0.75 or whatever. But the higher the number, the closer the number gets to +1, the more positive the correlation. The closer the number gets to -1, the more negative the correlation. Let's look at a couple of graphs now that explain that better. What we're going to look at now is a positive correlation. Now on this graphic here, I've got variable 1, which goes 2, 4, 6, 8, 10, 12, 14, and variable 2, which goes 2, 4, 6, 8, 10, 12, 14. And I think you can see I've got a data point there, there, there. These are all data points. Now what this is saying is when this equals 4, just over 4, when variable 1 equals 4, well, variable 2 equals 4 as well. Here we've got 10, and when 10 on variable 1 has a value of 10, then it's got the same on that one there. So what we're saying is basically is that as variable 1 increases, while variable 2 increases in a way which is exactly proportionate. So this is a perfect positive correlation. The positive correlation here is actually +1. It's a perfect positive correlation, because as variable 1 increases, variable 2 increases in exactly the same way. A positive correlation. And this is the shape of the graph that you get with a positive correlation. As long as the scales are running from a lower level there to a higher level there, and a lower level there to a higher level there, then positive correlation is indicated by a line of that type of gradient. As variable 1 increases, variable 2 also increases. A perfect positive correlation. And I'm just marking some data points onto this graphic. Now in this case, the scale is the same as it was on the last graphic actually. 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. But now, when the values for variable 1 are high, the values for variable 2 are low. So what we see here is that this particular data point here, well there it's got a value of 12, and on variable 1 it's got a value of 1. On this particular data point here, that's got a value of 8, and on variable 2 the value comes out at round about 5. So in this negative correlation, when the values for variable 1 are high, the values for variable 2 are low. It's exactly the opposite of the previous graphic. And the line this time goes down this way. This is a negative correlation. As the value of variable 1 drops, the value of variable 2 increases. Exactly the opposite of the graphic we've just looked at. And that line there gives us a perfect correlation of negative 1. So that's an example of a negative correlation. Now I'm just going to mark on some data points on another graphic here. And this one's a little more confused than the last one we looked at. But my overall impression is that, okay, there's a bit of an exception here and here, but generally there actually seems to be a positive correlation here. And what we can actually do is we can actually work out the correlation for these data points. So we can actually take two lists of numbers, and if we do that and we run it through a correlation statistic, we actually find out that the correlation here is plus 0.44. So these are positively correlated. And I can actually show you if we just go down and look at the computer's drawn this graphic for us. Again, I'll just mark on the data points so we can see them more clearly. So these are exactly the same data points. And the average best fit line for this set of data is pointing up the way. Okay, not as much as the 45 degrees we saw before, but this is a positive correlation, and it's of 0.44. So another example of looking at two variables, in this case variable 2 and variable 3, and finding out that the strength of the positive correlation between the two variables is plus 0.44. Here's another two sets of data points, or one set of data points really, on two variables. Now this time it looks like the general trend is going down that way. It looks like there's a negative correlation. And in fact, if we do a correlation statistic on that, we find that the strength of this negative correlation is negative 0.49. And if we actually draw on the line onto this graphic, again we can mark on the data points, exactly the same data points as before. And we do a best fit line on that, then we find that yes, it is sloping down the way like that, indicating that we have a negative correlation. In this case, a negative correlation between variable 2 and variable 3 of 0.49. Now here we have another bivariate scattergram. Again, we've got our data points, and we've got the scales, one variable there and another variable there. And the question is, can you see any obvious pattern in these dots? Well, actually to me they look fairly chaotic, they look fairly randomly distributed. Because what we have here is a scattergram illustrating that there's no real correlation between the two. So a best fit line might be somewhere in the middle here like this. So it's neither a positive correlation nor is it a negative correlation. There's essentially no correlation in this data set. Now here's yet another bivariate scattergram. Let's just make absolutely sure on this diagram that we understand what the data points represent. Now it's a scattergram of 33 11-year-old girls. And this variable here is looking at their height in centimetres, and this variable here looking at their weight in kilograms. And of course each data point represents one case. In this case, a single girl. So each red dot is actually one girl. So let's take this girl here for example. Well, this girl, we can see that her height is about 142 centimetres, 142 centimetres, and her weight, well, it's about 34 kilograms. So each data point represents a girl, and because it's a bivariate scattergram, each data point is giving us 2 pieces of information on each individual girl. Let's look a little further. Are there any girls who are very short but very heavy? That is, are there any in this area of the graph? Actually, I've used this area of the graph to put my title in because there wasn't any dots here. So we find out that there's no girls that weigh a lot that are also very short. Now, are there any girls which are very light but very tall? In other words, any girls in this area of the graph? Well, again, there's not. What we see, if we put a best fit line in here, is what we've already looked at. We seem to have a positive correlation. So we can say that in 11-year-old girls, there appears to be a positive correlation between height and weight. And again, I could use a statistical test, and I could have a figure of this. I'm not quite sure what it is, but the line would be somewhere like this. So maybe the positive correlation is 0.7 or 0.8 or something in that order. So we can say that for these 33 11-year-old girls, there is a positive correlation between height and weight. Really, it's not that surprising. What it's saying is that girls that are taller are more likely to be heavier. Girls that are shorter are more likely to be lighter. So weight and height appear to be positively correlated. Now, so far, the examples we've used might have been a little abstract. Let's now look at a much more meaningful example. This scale here looks at the amount of dietary fat consumed on average per day. This scale here, this variable here, looks at breast cancer deaths per year per 100,000 of the female population. So the 2 variables here are dietary fat consumed per day and breast cancer deaths. Now let's look at Thailand. Well, Thailand has got a very low amount of dietary fat consumed on average per day, and it's got a very low incidence of breast cancer. Japan consumes slightly more fat and has slightly more breast cancer. Colombia consumes slightly more fat and has slightly more breast cancer. Poland consumes even more fat and, well, it's got more breast cancer. Hungary consumes more fat, even more breast cancer. Norway, Belgium, and almost top, the United States and the United Kingdom, with very high levels of dietary fat and, unfortunately, very high levels of breast cancer. These 2 variables appear to be positively correlated. Maybe a best fit line would be something like that. Are there any countries that have low amounts of dietary fat and high incidences of breast cancer? Well, no, there aren't any countries that have low amounts of dietary fat and a high incidence of breast cancer. This part of the graph is empty. Are there any countries that have a low incidence of breast cancer and very high amounts of fat consumption? Well, no, there aren't. Again, this area of the graph is empty. And I've only put a few representative countries here. Actually, I could have put a lot more in. Most countries you look at do in fact approximately follow this pattern. There is in fact a positive correlation on every country I know of between dietary fat consumed on average per day and the incidence of breast cancer. So it does seem quite fair to say that breast cancer and dietary fat consumption are positively correlated. Now, if we accept that this is a genuine correlation, what does it mean about the cause of breast cancer? Does it mean that breast cancer is caused by dietary fat? Well, actually, all we can say, all any researcher can say, is that there is a positive correlation between dietary fat intake eaten in a country and breast cancer. We cannot jump from this observation or from the deduction of this correlation to saying that breast cancer is caused by consumption of dietary fat. All we can say is that there is a positive correlation. So it's kind of a rule in research that correlations cannot be used to demonstrate causality. To demonstrate causality, you must have more than a correlation. However, a correlation is very useful because it does tell you where to look. So this is an area now that could be subject to further research because it's an area that might have a causal connection. In other words, there may be a causal connection between dietary fat and breast cancer. We don't know. But this correlation in itself is not enough to tell us that. So whenever researchers demonstrate correlations, that's good, they can demonstrate correlations. But they cannot infer causality purely on the grounds of a correlation. So if a research paper you are reading indicates that causality can be demonstrated by a correlation, then the researchers are wrong. Correlations demonstrate correlations, they don't demonstrate causality. And let me just give you an example to illustrate that. There is actually a positive correlation between two variables: telephone ownership and deaths from coronary heart disease. There's a positive correlation between telephone ownership and deaths from coronary heart disease. Now, what this actually means is that countries that have more telephones, for example, the United Kingdom, France, Germany, Australia, the United States, Canada, well, they have a high incidence of deaths from coronary heart disease. But countries with low telephone ownership, such as Bangladesh, Nepal, Malawi, Zambia, well, they have a much lower incidence of deaths from coronary heart disease. So it is true to say that telephone ownership and deaths from coronary heart disease are positively correlated. But what it is not fair to say is that telephone ownership causes deaths through coronary heart disease. If that were the case, we'd have to advise people to get rid of the telephones because it's telephones that are causing coronary heart disease. Of course it isn't telephones that are causing coronary heart disease, but there is a positive correlation. Now, why do you think it might be that there is a positive correlation between telephone ownership and deaths from coronary heart disease? Well, you've probably realised that countries with a lot of telephone ownership tend to be the richer countries, the westernised countries. Countries with low levels of telephone ownership tend to be the poorer countries. And we know that there seems to be something associated with an affluent lifestyle which predisposes towards coronary heart disease. Factors like eating too much fat, not taking enough exercise, smoking cigarettes. We know all these are causative factors in many cases of coronary heart disease. They certainly influence the epidemiology of coronary heart disease. So can you see the telephone ownership is associated with it being a richer country, and it's the being a richer country which is associated with the higher incidence of deaths from coronary heart disease. So yes, telephone ownership is positively correlated with deaths from coronary heart disease, but no, it is not reasonable to infer that telephone ownership causes coronary heart disease. So correlations demonstrate correlations, they do not demonstrate causality. Now this graph, another bivariate scattergram, is showing an example of a negative correlation. And what we're looking at here is increasing child mortality, and what we're looking at here is the increased literacy status of the mother. Now this is not precisely numerical. We've got very poor, moderate, good and very good literary status of mothers. And here we've got child mortality. This would probably be measured in deaths per 1,000 births before the age of 4 or 5. And what we see here is that in mothers with poor levels of literacy, infant mortality is high. In mothers with good levels of literacy, levels of infant mortality are low. In other words, as one variable increases, the other decreases. So as the literacy status of the mother increases, child mortality decreases. A negative correlation. We could have taken other examples. AIDS is a huge problem. Now, the more couples that are monogamous, the less AIDS is transmitted. The two are negatively correlated. You could also argue the same for condom use. The more condoms are used, the less AIDS should spread through a population. You would expect a negative correlation between the two variables. So I think that's all I'm going to say about correlations. And I'm just going to show you two more graphics before we finish this session on descriptive statistics. And the first one, well actually them both, are about the reduction in the incidence of tuberculosis in the United Kingdom. Now here we see that from about 1861 all the way through to 1971, the incidence of tuberculosis was falling. But then, in about 1950, there was the introduction of mass radiography, X-rays, antibiotics, and the BCG vaccination. And we see that when these medical interventions were introduced, when the doctors and the scientists got their act together, they introduced mass radiography, antibiotics, the BCG vaccine. Well, the result then was quite staggering, and the incidence of tuberculosis fell to almost nothing. It became a very uncommon disease. And from this graph, doctors may well argue that it's a very good idea to spend money on high-tech treatments. Give us the money and we'll make the drugs, we'll make the vaccines, we'll invent the clever techniques and disease can be combated. If I wanted to make that argument, I would show you this graph. And it sounds reasonable because when the high-tech medical interventions were developed, the incidence of tuberculosis did indeed drop off quite dramatically. It was dropping off slowly, but that helped it to drop off dramatically. Therefore, my argument is it's good to spend money on these high-tech medical interventions if you want to fight disease. But is that a reasonable assumption? Let's just look at this scale here. Let's just go down this scale. Let's have a look at that. 2,000, 1,000, 100, and only 0 down here. This is a logarithmic scale. The person who designed this graph did it deliberately to try and point out the fact that these things were effective. Well, in actual fact, it had been falling off quite quickly here. So between there and there, well, that much drop on the graph represents a drop of about 500 cases of tuberculosis. Whereas this much drop on the graph here, well, that only represents a drop of 100 cases of tuberculosis. So maybe the arguments that the doctors put forward to get more money, because they said they were clever introducing X-rays, antibiotics and BCGs, is not quite as valid a claim as it initially appeared to be. Let's look at another graph now, drawn on a linear scale, and we'll see what the real position actually was. Now this graph actually shows exactly the same information. TB mortality here, between 0, 100, 200, 600, 1,000 and 2,000, but this time it's a linear scale. And again this shows the same years along this axis here, and here at the same time, 1951 or so, we introduced mass radiography, antibiotics, and we introduced BCG. And all of a sudden here, the drop-off, which looks so dramatic on the logarithmic scale, looks actually quite minor here. It's a very small drop-off. So on a linear scale, we see that TB was dropping really quite quickly. And the introduction of mass radiography, antibiotics and BCG, well, hardly seemed to make any difference at all, actually, if we look at it in the context of the whole graph. So always look at the scale, because the scale tells you a lot. So here we had a very sharp drop-off because some people wanted us to believe that. Here we had the real drop-off on a linear graph. Now, I'm not saying that medical interventions are bad. They're not. They're often remarkably useful, and we should spend money on research. This was just an example to show that graphs can be used, like so many different things in statistics, to illustrate what a particular vested interest wants it to demonstrate. We have to read critically to evaluate what is the good research and what is the bad research. Now, what was it that was causing tuberculosis in the United Kingdom to become so much reduced in incidence for 100 years, more than 100 years? Well, the reason the incidence in tuberculosis was dropping off very quickly, well, was dropping off anyway, was not because of drugs, not because of X-rays, not because of vaccines, but because of improvements in the way people were living. Because of improvements in housing, because of improvements in education, because of improvements in nutrition. It's the way people live, very often, that is the main determinant in how healthy they are going to be. So that's what I'm going to say now about descriptive statistics. Remember to remain critical. Remember to critique, to get out the truth so that we can apply the truth to the clinical situation.